two great talks by Evan Sadler and Asu Asadaglar. And now this afternoon, we're going to have one final talk by Eckles. And so Dean, do you want to start sharing your screen? And then after Dean talks, for people who are physically in Berkeley, I'll explain how we're going to organize lunch tables so that you don't have to be alone even if you're joining from your hotel rooms. But first, let's hear from Dean. Dean is going to talk about long ties, formation, social contagion, and economic outcomes. So go ahead, Dean.
Cool. Yeah, thanks for having me be part of this. I knew that this program was happening at Simons, and right now this academic year I'm on sabbatical and I'm in Europe, in Berlin right now. So wasn't really able to be part of it if it was going to be in person. So it's great to be part of this virtual event. So I was going to present kind of a couple of related things that are all connected by the notion of long ties, where what we mean here by long ties are connections in a social network where the two nodes that are being connected don't have any network neighbors in common, right? They don't have any mutual ties, right? And so those long ties could then be important for all kinds of things like the spread of information or disease or behaviors, and then could have cascading effects for things like economic prosperity. So the work I'm going to talk about, depending on how much time I end up having, is related to these three different papers. And really what I'm going to spend the most time on is the second one, which is kind of sort of like a network theory / applied probability / maybe applied game theory kind of paper in some ways. But we also have some empirical work that maybe is interesting, and that's the first and third papers. And I think talking about the first one will help to set up some of the ideas we might have about long ties and their importance overall. So, and I think also the first author of the first paper, Iman Jahani, is currently a postdoc and lecturer at UC Berkeley, and I think he's presenting some of our other work together during the poster session. So for those of you in person, you could connect with him. So kind of to set the stage of what do I mean by long ties and what's kind of the history of that concept in the social sciences. Strong ties are ones that are, involve a lot of time, a lot of emotional intensity, intimacy, reciprocal exchange. Maybe they're high bandwidth in some sense. There's a lot of information that can be transferred via strong ties. These are people that you trust a lot, et cetera, right? Those are more likely to be embedded in closed triads. So the people that you're, have the highest trust with, that you have spend the most time with, it's unusual if those people are not people that you share other contacts with, right? Actually, I think some work by Backstrom and Kleinberg highlighted some years ago that one of the best ways to figure out who somebody's significant other is on Facebook is to look at what's the edge that's most embedded. And they have some fancier measures as well, but that gets you a lot of the way there. What's the edge that really, has the most mutual ties and actually has the most mutual ties across a lot of different communities, right? So this is sort of a fact about strong ties, is that strong ties are also usually in these closed triads. On the other hand, weak ties, ones where there isn't a ton of time, there's not necessarily, these are sort of like arm's length relationships. These are more likely to be part of open triads. It could be that here in this picture at the bottom left, which is from a classic paper by Granovetter, A and B are connected, right? But B and C are not connected. And in fact, there's no one who is a mutual friend or mutual network neighbor of A and B, right? So weak ties are sort of more likely to be part of these open triads, though that's not their definition. Their definition usually is in terms of these things like time, intensity, bandwidth, trust, et cetera, right? And there's this idea that structural diversity, or having connections to a bunch of different local communities, having a bunch of these long ties could give you information advantages, could expose you to more sources of novel information faster, earlier, et cetera. So this is kind of the intellectual space that we're working in here and asking these kinds of questions. So do disease, information, and behavior spread more rapidly through more clustered networks left, where there aren't such long ties, or more random networks like on the right, where there actually there's a lot of long ties, right? A lot of the edges here are ones that have no embeddedness, or have zero embeddedness. They're local bridges. What local network structures are advantageous for individuals and communities? How do people end up with these different sorts of network structures? Why is it that some people have more long ties than other people? And what sorts of changes to network structure would accelerate the spread of contagions in networks? And really, I'm going to focus most on this first and last question, but briefly mention first some empirical work that we've done, right? So this is kind of the program, and then I'm going to say a little bit about long ties in the United States and Mexico, and kind of where they come from, and then spend a bit more time talking about how long ties can play a role in the spread of threshold-based contagions. Okay, so first, this empirical part. This is work that's we did in collaboration with Michael Bailey at Facebook. This is also with Iman Jahani and Sam Freiberger at the World Bank. But we're looking at a network connecting users on Facebook. And so we're going to focus on a network that's defined by mutual exchange of comments between people on Facebook. So this isn't just the Facebook network of people who say they're friends with each other, right? But it's a sparser network, and also a network that's going to have tie strength information associated with it. So there's an edge between users I and J if they've reciprocally exchanged comments during a 6-month period. Okay, so this is then we can actually use how many comments they exchange additionally as a measure of tie strength, and then we can get estimate for most people where they live in the U.S. or Mexico, and that's going to be important for doing things like measuring the prevalence of different kinds of network structures in particular places. And so,
Dean, did you want me to interrupt with questions that people?
Sure.
Okay, so Ben asks, does this include comments like on a political post, strangers arguing with each other on the internet?
So these are subsets of the declared friendship ties. I think I should maybe clarify that. So it could be that there's a public political post by a political figure, and then I comment on it, and then you reply to it. And if we're Facebook friends, that would count, even though it's not on a post by either one of us, but it is the subset of the friendship ties. Yeah.
Great, thanks.
So a lot of the analysis that we do with this is actually at the individual level to avoid issues of ecological fallacies. But I think the geographically aggregated level helps provide a lot of intuitions, and the results end up being quite similar, and it allows us to make some pretty maps. So I'm going to start with the geographically aggregated version. So nodes within a region have ties to other nodes in that region and also to nodes outside of that region. And we can say, just of all ties that involve the nodes in some region, like a zip code, what fraction are long ties? We're here to spell this out. Long ties are ties without mutual neighbors. These are sometimes called local bridges, and we'd say that they have edge embeddedness 0. And so we can just look at what is the fraction of long ties look like across US counties. Here's aggregated up to the county level. And this is after partialing out average degree, because just how many connections people have is quite related to this fraction of long ties. And so here we see, that some places in the US just have a lot more of these long ties than others. And so notably, you might look at, say, Appalachia, and notice that Appalachia has a very low fraction of long ties. Whereas in a bunch of places, kind of, wealthy suburbs, et cetera, have a lot of long ties. In general, much of the American West has a lot of long ties by comparison. Okay, you can similarly look at this for Mexico. Depending on your knowledge of the US versus Mexico, this might also allow you to think about some of these specific places. And some of the places with indeed the lowest levels of long ties in Mexico are also economically not so prosperous. Okay, So you can then think about, okay, this is just this prevalence of these long ties. And we asked two questions in this paper. One is like, what are some life events that we think might create these long ties, both directly and help people perhaps develop the skill to form these long ties? And then is having these long ties associated with economic outcomes, right? Part of the theory coming from this rich work in sociology is that these long ties would give people access to a whole bunch of additional information and opportunities that they wouldn't have if they have a network that consists of much more closed triads rather than this kind of open structure. So we do look at how in the paper we focus a lot more on the individual level outcomes, but I'll just again show the geographically aggregated version here. Just looking at how the economic outcomes for a zip code in the United States depends on the fraction of long ties in that place, controlling for a bunch of other things like degree and population, et cetera, right? So this is what these typical results look like here, is that places with a higher fraction of these long ties, so more of the ties that involve the people in that place don't have mutual neighbors, the higher median household income we have. And these results, we have very similar results for unemployment, lower unemployment with a higher fraction of long ties, and all kinds of other thresholds on income. Intergenerational mobility is also higher in these places with this higher fraction of long ties.
Do you have any way to claim causality here?
No. I would say that, that we want to be kind of careful about that. That I would assume that there's actually causal processes running in both directions, right? Long ties can kind of be expensive to maintain, right? One way to maintain a long tie is to see that person in person, and they might. Long ties are not defined geographically in our definition, but they're more likely to be farther away geographically. It also can be that, say, if you have a bunch of people with, that are all connected to each other, you can do something like have dinner with all of them at once, or have a social gathering at one of their homes, right? And everyone is sort of welcome in that setting. Whereas long ties might be more expensive to maintain. Maybe I need, in terms of time and money, right? I might need to actually have dinner with these people separately. And if we're going out to dinner, maybe that's expensive, or we have to sort of arrange things so that we're having social gatherings that kind of are appropriate in that way. So, I think causality kind of runs in both directions, and that we're not looking at the fraction of long ties that formed in some earlier prior period and looking at these later outcomes. I mean, especially with economic mobility. Right, some of those economic mobility events are happening prior, probably, to some of these relationships even forming. So, yeah, I'd say this is what we find to be a very robust association, whether it's at the aggregated level or at the individual level, and using a whole bunch of different kind of outcomes we measure. But yeah, we don't think that this result is something that we would attribute to a causal relationship, a single causal relationship. And I think it's actually even interesting, and in some of our other work together, Iman Jahani and I have worked on this, is thinking about what are the causal effects of network structure? What kinds of interventions do you actually have in mind, right? Because if I were to say, oh, but I wanted to claim that, yes, increasing the fraction of long ties is going to increase median household income. What am I even saying there, right? Like, what kinds of possible interventions to network structure do I have in mind, right? One way to increase your fraction of long ties is to make two of your friends have a falling out with each other, right? Is that beneficial? I don't think so, really. Like, so we want to have particular kinds of ways of changing the network structure in mind. Yeah. So one of the things that I mentioned earlier, right, is this idea that a lot of times weak ties have been kind of thought of as just another name for long ties, and vice versa, right? But we really think of it as that it's the long ties that are kind of important here, right? Now, long ties happen to be more likely to be weak than, short ties. Strong ties are likely to be short, right? But it could be that you give more of your attention or time or emotional intensity is directed at people that you don't have, common network neighbors with.
Dina, Rachel Cranton in the chat asks, are there gender and or age differences in these patterns?
Yeah, so yes, there are some of those differences. A lot of those things are also related to degree. So people of different ages have accumulated different numbers of friends. In the United States, in particular, women have higher degree on Facebook than men do. And so then that is really closely related to these outcomes. And I'll show later briefly a slide that shows how strongly related to degree these measures are. But in a lot of what we do, we're able to at least do things like match on age and gender, but we don't specifically study that as a source of variation here. It's more, it's a nuisance, I guess. Yeah. And we'll see that we look at a couple of kind of life events that, and so you can see how people could accumulate these ties over time. So we really want to say that it's the long ties that are predictive. And in fact, if you could put more intensity, more bandwidth on the long ties, therefore, kind of breaking the weak tie, long tie association in some sense, that could be beneficial, or at least it could be predictive of these better outcomes. And so we see that actually, if even conditional on the fraction of long ties in a place, the weighted fraction of long ties, that is weighted by the number of comments that are exchanged on that tie, is also further predictive of median household income in the same direction, right? So conditional on just how many long ties you have, if more of your attention, more of your interaction is allocated to those long ties, that's also associated with better economic outcomes, okay? And this also holds at the individual level. Here in the 6 largest states in the US, if you look at the fraction of long edges, this is associated with both people's zip code level median income, but also some other proxies for economic prosperity, like how many different devices they use to access Facebook. Similar results for also the price of the main mobile phone that they use. Also how many donations they make using Facebook's donation product, or even donate to charities and directly to people. And a similar thing applies for the weighted fraction of long ties. So basically we find this robust empirical association between whether it's individual level or zip code level network structure, the presence of these long ties and these stronger long ties, and economic prosperity. So yeah, I wouldn't want to claim that this is this kind of simple unidirectional causal relationship, but this is kind of a robust correlation that we think is an important stylized fact to consider and further study as well. Also, it's not kind of the only thing in the picture, right? I think earlier Nicole referred to these recent pair of papers in Nature by Matt Jackson and Raj Chetty and others, and that looks at one other kind of network structure measure that is quite related to economic outcomes and mobility, which is the degree to which people who are lower income and higher income, or lower SES and higher SES, are connected through the Facebook network. We might think that actually a bunch of these long ties that people have are more likely to be those sorts of SES spanning ties as well. So just to say a little bit more about this, one of the things we thought was interesting is, where do these ties come from, right? So why do people have more or less of these ties? So we looked at 3 life events that people can have that are all kind of disruptive life events, right? That are all changes. You could think of these as mobility events, or migration events, people who migrate between states or attend college in or out of state. I don't have time to go into all of them. I'm just going to focus on people attending multiple high schools, okay? So In part, we think this is a nice one because people who change high schools maybe don't make that choice for themselves. Their parents might be making it, might be made for various reasons that are sort of somewhat out of their control. So we've got people who are aged between 30 and 60 and have some of the available data who either list a single high school or two high schools in their profile. And we match on age, gender, hometown county income. And people who attend multiple high schools have 10% more in relative terms, long ties, relative to those who attended a single high school. This is true at basically all levels of degree. If you stratify by degree how many total connections they have, you can see on the right here that just the long ties fraction is just always higher for the people who attended multiple high schools. If we try to eliminate all the ties that are associated with either of these high schools, you also still see this pattern, right? So the idea that we have in mind is not just that this event maybe is immediately producing more long ties, but that also it's potentially helping people to develop a disposition to form more long ties in the future. One thing we're able to do with this that I haven't added to the slides here yet is that we actually look at a kind of exogenous event that occurs where or plausibly exogenous at least, where a school closes. And if you look at the people, in kind of a diff and diff setup just before and after a school closes, the people who were exposed to that closure also have a higher fraction of long ties. So again, there could be various sources of kind of confounding here, but we think that, even in that kind of a case, that it's interesting that this association persists. Okay. So, given those results, this is kind of consistent with this whole broad story about the idea that long ties, structurally diverse networks are advantageous for people because they give them access to information and opportunities, et cetera, right? It seems useful to think about how does that square with the kind of models that we use to think about the spread of information and behavior in networks. Okay, so if we think about like what's sometimes called a simple contagion, this is a model where if someone is infected with a disease or has some information, that they're going to pass that to each of their neighbors with some probability. And so that means that if I have some number X of infected neighbors, my probability of becoming infected in the next round or receiving some information in the next round is some kind of sublinear function of the number of adopting or infected or information having neighbors. Okay, so then in this kind of setup, these contagions are just pretty straightforwardly accelerated by doing things like rewiring a network. If you start with a really clustered network like a lattice and you just do random rewiring of edges, that's going to speed up these sorts of contagions. So long ties accelerate these kinds of simple contagions. We're all sort of familiar with the idea now, right? That in the early stages of an epidemic, it can be a good idea to restrict travel because some of that travel is all about long ties, right? Okay. So long ties accelerate social contagions too, right? But I think the story in the literature has been a lot more complex than that, coming from kind of multiple prominent papers. So Santola and Macy, sociologists say, for complex contagions, which they think are quite prevalent, too little clustering means too few wide bridges, which not only slows down cascades, but can prevent them entirely, right? Montanari and Saberi in PNAS say it appears that innovation spreads more slowly on well-connected network structures dominated by long-range links than by more clustered, say, geographically clustered networks, right? And what they have in mind in terms of the models of contagion here are models where basically there's some probability, there's some threshold above which I have very high probability of adopting, compared to below the threshold where I have very low probability of adopting it. And generally what they're studying here is this deterministic model where there's just some threshold or in general, we'll think of this being threshold as being theta, above which I adopt, and below that threshold, I don't adopt. Right. So now what we're going to consider here is cases where this threshold is not entirely deterministic, and see how this kind of changes some of the landscape of the results, right? So what we're thinking about is, this kind of a model of contagion on the right that could really be rationalized as some kind of myopic best reply play in a semi-anonymous graphical game with strategic complements, right? So you can imagine that if I adopt, I get some utility that's proportional to the number of neighboring adopters I have, and I'm playing some kind of myopic best reply. So one thing to note is that there doesn't really seem to be much evidence for anything like a deterministic or near deterministic threshold in the empirical literature, okay? So if you look at the from empirical papers, the probability of someone adopting when they have exactly k neighbors who are adopters versus probably adopting when they have k minus 1 adopter neighbors. If there was like a clear threshold in the data, right, or at least a homogeneous threshold, you should see really large values of this ratio somewhere, right? But it seems like the largest values we see anywhere are like 4. Even in some of the work that's actually argued for the importance of these kind of threshold-based complex contagions, these ratios are often under 2. For example, if you think of this case from Centola, there's just, the ratio is actually under 2, so it's really a sublinear kind of curve to some degree. So I think there's far from being evidence that these thresholds are kind of these really homogeneous and deterministic kind of thing. So we're going to study a more realistic model with a small probability of adoption below the threshold. You can think of this as kind of noisy, myopic best reply dynamics, or that there's sort of trembling hand adoptions happening. In a bunch of the results, we focus on the case of a threshold at 2, right? So if I have 2 adopter neighbors, I adopt. And then if I don't have 2, if I just have a single adopter neighbor, I could adopt with probability Q. And Q is going to be some small value. And actually, we're sometimes going to only allow that probability Q to happen via some edges. So it'll only be some particular local ties that could infect me with this probability Q. And we'll see that having Q greater than 1 over square root of n is enough to really change the landscape of results that led to this idea that long ties are weak for complex contagions and are insufficient to facilitate their spread. Okay. To give you a kind of tour of our analytical results, we're going to look at time to spread of a deterministic threshold-based contagion when random edges are added to a lattice. This is going to just help sort of fix some ideas and provide some preliminary results. Then we're going to think about what happens if we're substituting random edges for these clustered lattice edges. For these analytical results, we use these kinds of graphs. So a cycle power K graph, where you just have all the nodes connected by a cycle, and then they're connected not just to their immediate neighbors in the cycle, but to further neighbors than that, right? So in C2, you're connected to not just your immediate neighbors, but their neighbors as well. Then we're also going to think about cycles that are combined with a random graph. So CK 2 over n is going to be the union of CK and a random graph with edge probability 2 over n. Okay, so these are going to be kind of like small world networks, so not exactly the Watts-Strogas network, and there's also some versions of this that are not exactly some other like Newman-Watts versions of this, but they're very similar to that, but they have some mathematical advantages for us. Okay, so let's just think about adding ties to some cycles. So we have C2, and we have this contagion with this threshold 2 that's spreading on C2 from 2 initial points, okay? So then we add some random edges. So maybe in this draw, we just get this 1 random edge, okay? Drawing this 1 random edge, this can only reduce time to spread even with a deterministic threshold, right? Because adding edges in this kind of a model is just only going to speed things up. So spread time on C2 is order n. It's got to just go around this whole circle, right? Whereas spread time on this network where we've added some of these random edges can actually occur with high probability much faster than that, okay? To give you a sense of what are the mechanisms of spread, why is this happening intuitively? There's going to be these 2 initial adopter nodes, and then things can spread along the cycle, okay? And then eventually the cycle is going to be large enough that there's some other node that has two edges to that infected cycle. And then it's going to pop over to that place. And this actual draw that happened to also coincide with one that was 3 edges to that section, which is maybe a little confusing, but usually it would be 2 edges, right? So then the contagion jumps to this one point, and then it can potentially start growing from there as well. Okay. In the case that we still have C2 in place, it's going to grow just through above threshold adoptions. Okay. But if we allow some below threshold adoptions, the idea that you could adopt with probability Q, even if you only have one adopter neighbor, then some of this spread along the cycle is going to happen via these below threshold adoptions. So starting from a pair of adjacent C1 neighboring infected nodes, it's going to take these, no, this is the result I just showed you. Okay, so but now I actually want to replace the cycle edges with random edges. So what if we go from C2 on the left to C1 union with a random graph where we're going to have the same expected number of edges, same expected degree, et cetera. Okay, and so really this is going to trade off 2 things. One is that we have to wait until these cycle intervals get big enough. And then once they're big enough, with high probability, they're going to start new intervals in other parts of the graph. Okay. So we can up or bound the spreading time by breaking down the contagion into those 2 subprocesses. And so, when is it going to happen that with high probability, there is some uninfected node that has 2 edges to one of these infected intervals? That's going to happen when an interval is square root of n log n nodes long. Okay, so that helps give us this sense of how long do we have to wait for these intervals to grow, and they're growing just through these below threshold adoptions. Okay. So that then tells us that with high probability that we're going to have this contagion spread to the whole network when n is large, in less than this amount of time. And you can see that this depends on this square root of n and q. And so when q is larger than square root of n, then we're going to end up also being asymptotically faster than the spread in C2, where it's order n. You can see this also in simulations as well. So, whether you do it with exactly this kind of model that we described or similar logit or probit models. You can also do this with sort of interpolating between C2 and C1 union with this random graph. So maybe we want to not just completely switch from C2 to this to C1 that with these random edges, which is much more random. What happens if we just sort of are making smaller changes to the network structure? Is that going to have the same effects, right? And so we can do this by defining this network where we rewire some number of edges, and we're still basically keeping the node degrees more or less the same as we do this. And so what we end up finding here is that you just basically need to rewire enough. If you only rewire a few edges, then you might break some of the structure in C2 that's allowing this contagion to spread around the network through this above threshold adoptions, while not creating enough long ties that you're going to have these long ties that you need for intervals to form new intervals in other faraway parts of the network. So basically in this setup, you need to rewire at least half of the edges, right? So you need to get to a sufficiently random network. We find that in empirical networks, you're kind of already random enough. And so any real changes to the network structure are going to speed things up. Everything I've said so far is about a contagion that doesn't reverse at all, right? That once you adopt, you remain an adopter. I think this is actually a pretty important conceptual thing to think about, right? Some behaviors, you kind of switch back and forth between multiple available behaviors at any time. If you're bilingual, depending on who you're talking with at the moment, you might switch between speaking English or Spanish, right? And you could just switch back relatively costlessly. Sometimes this can get a little tricky. You might mix things up, right? But like overall, you can switch pretty easily, right? Once you learn Spanish, you don't have to only speak Spanish for the rest of your life, right? You can speak whatever other languages you speak as well, okay? But for a lot of things that we study in terms of the spread of behaviors, there's there's not just like immediate costless switching happening, right? If I decide I'm going to buy a hybrid car because everyone's getting hybrid cars, right? And maybe there's a better charging network if I get an electric car, right? Then I don't just suddenly the next day decide that I'm selling my electric car. Similarly, if I decide to install WhatsApp, then I still have WhatsApp installed. It doesn't just sort of go away. I don't just sort of reevaluate in the next period. Okay, so I think it makes sense to have there be substantial inertia in contagions, where once somebody adopts some behavior or product, maybe they stick with it for a bit, but they could revert with some probability. So if we allow adopters to revert with a probability delta, you can think of this as also upper bounding the time if adopters just reevaluate what they're going to do with probability delta in each period. Then generally we get the same results that we had before, except that delta needs to be smaller than 1 over square root of n, and also it's really our results are going to end up depending on the difference between q and deltas. Q is this probability of adopting spontaneously, and so now we need q minus delta to be larger than square root of n to get these results that these more random networks are speeding things up. So I think this is actually kind of just more generally an interesting point, is that this question of is the contagion reversible or not doesn't come up if you think about like the initial deterministic threshold-based contagion, because no one ever has a reason to change their decision, right? Once you adopt, right, it's just this progressive contagion. And so even if somebody reverts, they're always going to make the same decision again in the next period, if no one else is also changing at the same time, right? So whereas if you start to consider this some kind of non-deterministic process, then this becomes relevant. And one of the things that we realized in this is that some of the prior work that I mentioned, when they have studied non-deterministic contagions of this kind of these threshold contagions, they're always perfectly reversible in that everybody remakes their decision anew in the next period. So if somebody who has only one adopter neighbor adopts, right, it's very likely that then in the next period, they're going to decide not to adopt again, because there's no inertia in that process. So that's part of the reason that these earlier papers by Montanari and Saberi and Santola and Macy, I think, find that, oh, their results are robust to, some kind of stochastic aspect to this, but it's always with no inertia whatsoever. Okay. So
just a heads up,
I want to
there's like 5-ish.
Yep. Okay, cool. Yeah, so I was just going to conclude with showing some of this applied to empirical networks. So I'm just going to do some simulations on a whole bunch of different empirical networks where we think about time to spread under 3 interventions. So first we consider how long does the contagion take to spread on the original network? How long does it take to spread if we do some random rewiring? What if we randomly add edges? What if we randomly add edges that close open triads? So that's like actually preferring to add short ties, right, as opposed to long ties. And here I'm just going to focus on a 10% intervention, where basically we're doing this to 10% of the original edges. Okay, and we allow below threshold adoptions here with probability 5%. If that seems large to you, you can also think about the fact that if people don't actually adopt with probability 1 above the threshold, really what matters is the ratio of this probability above the threshold to the one below the threshold. So we're talking about the below threshold probability being, a 20th, right, of the above probability threshold. Okay, so the first set of networks that I'll show you are these networks that maybe a lot of people are familiar with, which are measured among households in rural villages in China, and edges indicate that these are people who they discuss farming and personal finance with. We're using the undirected version of this network. There's 175 of these villages. Okay, so first, just thinking about the original villages, the original village networks. What if we run this spreading process on them? So here, each of these lines is the CDF of time to spread for one of the villages. And then I've normalized them so that the mean spread time is 1 here. Okay, so we can see that, some of the villages things spread a little bit faster or, slower in, but we've removed that variation. Some of them have a little bit more variance from simulation run to simulation run and how fast things spread. Okay, now we're going to consider some of these interventions. So what if we rewire 10% of the edges at random? Okay, these curves basically all shift left, right? We've just reduced the time to spread. Okay, so random rewiring here is speeding things up. Now this says that, to the extent that our theoretical results are a good guide here, part of the idea is that these networks were sort of already random enough that a little bit of random rewiring is moving us in the right direction, right? Because we saw before that if you're sort of interpolating between C2, say, and C1 union with this random graph, you need to be, sort of halfway there already for, going more random to help you. So we're seeing here already that just rewiring speeds things up. Maybe it's more realistic to consider interventions where we're adding ties. I said before, it's not like we want to consider interventions where we make, your two friends have a falling out with each other, right? Or we change the existing edges. Maybe it's more about encouraging people to make connections, sort of along the lines of some of the random squadron assignment stuff that Evan was talking about. This is this time when people are arriving and forming connections. So what if we close triad closing edges, right? So these are adding short ties. That's going to speed things up relative to the original network, which is just more edges, right? But if we were to add random edges, that would speed things up even more. Okay. So basically across these 175 networks, if you look at the difference in ECDFs, so for each of these lines on the left is the difference in the CDF for spread times under adding random edges versus triad closing edges. You basically have stochastic dominance, right? Adding random edges rather than triad closing edges is just shifting this distribution of spread times lower to be faster for pretty much all of these 175 networks. And if you look at this across a bunch of other collections of networks, you basically see similar patterns. The magnitude of the effects can vary, but it's the same pattern across all of them, that rewiring some of the edges or adding random edges instead of adding triad closing edges is speeding up the spread. So I think I'm pretty much out of time. So I'm just gonna kind of summarize by saying that I think biological contagions, we know that, and spread of information are sped up by having these long ties. And social contagions characterized by a noisy threshold for adoption also are sped up by them. So it's kind of this nice harmonization of what seemed like these very different models of spread. And so it kind of give us a similar story about what changes to network structure would do. These are I didn't talk about this third paper, but these are the two papers I talked about. Especially, I was just talking about the second one here. I'm happy to stick around for comments or discussion or get any of your feedback offline about this as well.
Thank you. That was fantastic. We can all virtually. Yeah, we have some time for questions. If anyone has any questions, you can navigate in the physical or virtual world to the podiums to ask your questions or the mics. Grant.
Yeah.
I think you have to navigate to this podium, sorry.
I'm not sure this is a well-formed question, but I guess this idea of reversion was kind of interesting to me. And I wonder, what kind of processes we're thinking about, if there's processes with high reversion, like I get into an exercise routine and I'm likely to fall back, if things would change and these strong ties become maybe more useful, or if you think that's not quite the right story.
Yeah, I think that's interesting. Cases where it's very likely that people revert. Yeah, I think some of those, it's hard to, if reversion is high enough, I guess maybe it's interesting to think about, okay, what's the part of the parameter space where you have really high reversion and actually something is realistically going to spread very far. Now maybe that is possible, right? So I mean, what we would have in mind there,
where reversion is lower when you have more friends that are doing it. So there's kind of like,
right?
New exercise routine, I have 10 friends, I'm maybe less likely to revert than I have 0.
Right. And I think some of that, like, I mean, some of it, we think about reversion as just a way of upper bounding the spread time for reevaluation. So you could just think you reevaluate it and then you decide to continue doing it, you know, if you have at least theta, which on all the examples I showed was 2 adopter friends. Yeah, I guess it, you know, it'd be interesting to see, yeah, maybe what additional evidence, empirical evidence we could bring to bear on that, because thinking about like the empirical evidence that we have this for initial adoption there, you don't really see anything so striking in that way, but maybe there's something about adherence that's interesting. That's a good, maybe a good impetus to look at some of the empirical stuff.
Vahide has a question in the chat. It's the Facebook data during COVID. If so, is there any effect of difference in the likelihood of remote work across income spectrum?
Yeah, that's interesting. So yes, this is, you know, in some sense during COVID, you know, I kind of wonder what that question is going to mean in you know, when people are asking about 2022, I don't know. Right. Anyway, yes, it is in the period that you mentioned there. And yeah, I think that we know that did change people's behavior online. I think, I mean, just drawing from like, you know, the public reports from a bunch of the social media companies said, oh yeah, like usage is up, et cetera. And so I would imagine that then usage was up in a whole bunch of kind of systematically kind of different sorts of ways. I didn't really go into this, but we do focus on people here who at least have some baseline level of usage. And so they have at least degree 10 in this comment network. So that's somewhat dealing with that. Then also, because we're conditioning on degree, that's also kind of like conditioning on this some measure of activity. And then finally, in the analyses involving the weights that are like the counts of comments that are exchanged, we also are conditioning that is like matching in various ways on the sum of all of the weights. That is just the total number of comments that they produced during that period of time, or the total number of comments they produced during that time. So that you know, is in some way adjusting for that, but we didn't specifically look at how that could be related to that. My sense would be that a bunch of this pattern would be kind of robust to that period, but certainly I think, you know, it'd be nice to have this be a kind of rolling data set. Our intention, like, you know, maybe not nearly as ambitious as what Matt Jackson and colleagues did with the socialcapital.org, is to make this geographically aggregated data publicly available. And so then, you know, perhaps as part of that, it would be more something that could be updated at future times as well.
That would be fantastic. Great. I think if there are no other questions, I will just make a brief announcement. Thanks, Dean, for this fantastic talk. If you want to talk to Dean, you know, you can approach him in the auditorium. For those of you that are in person in Berkeley, but you know, virtually on the platform, if you want to have lunch with other people, we can coordinate lunches by getting into a group and discussing where to go. So I would recommend everybody that's physically here and wants to join a lunch group, navigate to your avatar to the left. There's a gray rug and it says you are in the main seminar room. So if you navigate your avatar to the sort of west side of this room, you can coordinate lunch. I see Ben Golub is already standing there. There to coordinate lunches. I'll watch you. And if you want to talk to Dean, he's in the table in the southeast corner. I guess Ben doesn't want to go because he's running away. Oh, he's running over to talk to Dean. This is fun. It's like a, you know, what do they call those? Sports commentator. I'm a sports commentator for what's happening on the platform. Great. I think poor Alex wants to go to lunch with somebody. Nobody's. Alex, why don't you go to the table where Dean and Ben are and see if you can convince Ben to go to lunch. Or yeah, if you're on mute, but did anyone in this room want to go to lunch with Alex?
Well, I have a proposition. I have a car.
Oh, you can come up here. I think Alex will hear you.
I would,
You have a car?
and we could get take up from Greg R's and drive up to Tilden.
Wow, that sounds fantastic.